Welcome back to ME 3710. Today's lecture is going to continue on looking at external flows. Now we're going to move specifically into lift and drag. We'll start with drag force because it is kind of a logical continuation to what we were discussing when we were looking at pressure gradients and separation of the boundary layer, because it plays a huge role. These boundary layer characteristics play a huge role in why we have drag, different types of drag. We talked about, and now this kind of, the basis for this comes from the work that we've done on drag dimensional analysis. So for example, if you recall, our drag coefficient is equal to the drag force divided by 1/2 rho v squared a, where a was the projected area and v was the velocity that was characterizing the flow situation. So if they flow around a cylinder we were looking at. So, and we kind of need to be careful when we talk about drag coefficients, because oftentimes people will say, well, it's got a low drag coefficient if they're talking about a car or something like that, but that doesn't necessarily mean that the drag force itself is low. So we have to think about that carefully. So here I have a link to one of the MIT old school videos that I like to show, and I highly recommend that you take a look at it. There's lots, and if you're interested in drag, there's lots of great videos and experiments that are run in there, and I encourage you to look at it. In fact, now we will look at part of one right now as part of an illustration. So I wanted to start out with a mental exercise, and our mental exercise is going to be looking at these two different shapes. So a sphere or a teardrop shape. This teardrop shape is my poor PowerPoint art version of, say, something that might look a little bit like a bomb shape or an airfoil shape that is basically tapered. And the question is, which shape has the lowest drag force? And so so write down what you think based on your intuition, and maybe even scratch down why you think that's the case. And what we'll do is we're going to go to one of these MIT videos and have a look at why, or at least maybe try to answer this question in part. So we're going to move over here to around 1536. And this is the... All right. Hopefully you'll be able to
For the second of our pair of related experiments, we use these two tubes containing the same viscous liquid, glycerin. I am going to drop two models simultaneously, one in each tube, to see which goes faster. Here are the two models. You see that they are small-scale replicas of the models used in the wind tunnel experiments. One of them is a smooth spherical ball. The other is a bomb shape, having exactly the same maximum diameter as the ball. In the wind tunnel, the two models were mounted on an equal arm balance in such a way that they had the same net weight in air, the fluid in which their drags were being compared. These models also have the same net weight, not in air, but in glycerin, the liquid in which they are to move. In the wind tunnel experiments, we compared the drags of the two bodies at the same speed. In the liquid, however, we should compare the speeds of the two objects when each has exactly the same drag. Now, when we drop an object like this steel ball into a liquid, it at first accelerates. But as it moves faster, the drag on it increases, until after some time it moves at virtually constant speed. This ultimate speed is called the terminal speed. Here is a stroboscopic photograph we made a short while ago. The time interval between exposures is constant, and so the distance between successive positions is a measure of the speed at successive instants. You see that there is a zone of acceleration which gradually merges into a range of constant speed. Now, and this is important, when an object moves uniformly at terminal speed, the sum of the forces acting on it must be exactly zero. At terminal speed, therefore, the drag acting on the object must exactly counterbalance and be precisely equal to the net weight. You see that the two models do have exactly the same net weight in glycerin, and so they have exactly the same drag when each moves at its own terminal speed. If the terminal speed of one is greater than that of the other, it offers less resistance to the flow. Now let us recall that in the wind tunnel experiment, the streamlined body offered less resistance to the airflow. At the same speed, it had less drag. The question now is, will it also offer less resistance to this viscous liquid? For the same drag, will it have more speed? They're already at terminal speed. Since these are plastic models, they drop much more slowly than the steel ball we dropped a moment ago. The answer to our question is no. For the same drag, the streamlined body has less speed. Conversely, if we were to make experiments at the same speed, we would find that the streamlined body has more drag. This result is just opposite to what we found in the case of the airflow. And once again, matters look complicated. Let us review.
Okay, so I can encourage you to have a look at that video again online yourself. If in fact, when this version of the YouTube of my YouTube lecture has low quality resolution, I apologize. But go back and take a look at that video, and you'll see that in fact the sphere had lower drag than the teardrop shape. But he did refer to the airflow experiment where the teardrop shape had lower drag than the sphere, which probably is what you would have guessed in your exercise before, because why do we make a teardrop shape? We use it to reduce drag. Now, so the answer to the question is it depends. And what does it depend on? It depends on the Reynolds number. That is the dependence of our ratio of viscous to inertial forces. So what also happens as a result is if we have a very, very low Reynolds number problem, then our drag is going to be dominated by shear. That is, all of these little, say this is dropping downward like this, there's going to be a little shear stress acting along the surface, the friction. And same thing's going to happen here. We have friction acting along the surface of the sphere, but which surface has a higher area? Well, this bomb shape has a larger surface area. And that larger surface area with friction acting along it is going to act to retard the teardrop shape under a low Reynolds number situation where shear stresses dominate the drag. If we do it in air, so shear is going to dominate in, say, glycerin, where we have low Reynolds number, but in air, we're going to have pressure drag dominating, and as a result, the drag force will be much lower on the teardrop shape than on the sphere. So this is kind of a neat, maybe non-intuitive result, and it's going to be you need to note that the drag force in low viscosity fluids will generally be dominated by pressure drag. That low viscosity fluids that we'll be dealing with at relatively high speeds, and when I say relatively high speeds, I mean high Reynolds numbers, are going to be dominated by pressure drag. Very low Reynolds number problems, usually associated with high viscosity fluids, are going to be dominated by shear. And this is going to definitely change our concept and how we think about these types of problems. Remember that both air and water are examples of relatively low viscosity fluids. So we'll expect in our typical day-to-day life where we work with water and air that we're going to have a lot of times bluff bodies, like shapes like cylinders or discs or cubes. These, or most vehicle shapes, these are going to be dominated by pressure drag. So what do we mean? So these drag forces that we're looking at, here's an example on the bottom of a top-down view of a cyclist. He's got the wheels in the front and the back, and we have the flow coming around it. And we have both pressure acting normal everywhere along the surface. These are pressure forces. And then we also have the shear stresses at the wall that are acting along the surface. And our pressure drag that we were just talking about, that's going to be equal to the integral of all of the pressure forces acting over the object. And so if we end up having if we're moving from left to right, this aerodynamic drag that we're going to have, we're going to add up if we have more pressure forces acting from left to right than from right to left, we're going to have a net force that's acting to the right, which is going to act to slow us down. And the same thing is going to be the case for our shear stress. The difference for a high Reynolds number case is that the shear stress is going to be less than, the shear stress component of drag is going to be less than that of pressure drag. So here in our case that we're looking at for a cyclist that's riding in the air, the shear stress component, or the sometimes called the skin friction drag or the viscous drag, is going to be much smaller than the pressure drag because this is a high Reynolds number problem. And in this case, you can do a quick estimate of this, but typically problems will have like a flow around a person will have in the air will have a Reynolds number, say of 10 to say the fifth. So it's very, very, very high Reynolds number. So what about just the drag coefficient over a flat plate? This is not a bluff body. We were talking a little bit about this in last lecture, and I just want to kind of remind you about this before we continue on through all of the bluff body flows. On the right-hand side here, we have a figure that shows non-dimensionalized, so U over U infinity, or U over the free stream flow. So if we have given, usually I call it U infinity, but we have our boundary layer that's growing. Out here we'll have this big U, and then inside of the boundary layer we'll have our profile of little u. And then our non-dimensional coordinate y over delta. So these are our velocity profiles. Of course, at the free stream, the velocity must go to u infinity, or the free stream velocity, capital U here. And so they both a laminar and turbulent flow go to that, and you can see quite a large difference. And one of the big important points is that this slope down here at the surface is much steeper for the turbulent flow case than it is for the laminar flow case. And we remind ourselves that the shear stress at the wall is going to be equal to mu du dy at the wall. And for the turbulent case, that is going to be much larger than the laminar case, in which case that means we're going to have higher shear stresses at the surface. And since we don't generally have a separation over our flat plate, it's possible we could make it happen, shear stress is going to dominate the drag. And so our drag coefficient is going to be dominated by the shear stress at the surface. So if we integrate the shear stress over the surface like we talked about last class, we can get our drag coefficient. And the drag coefficient that we have here, you can see there's some these curves on the left-hand side, and they're going to be dependent on roughness. So here, epsilon is our roughness length, and L is the length of the plate. And if we wanted to write down what the Reynolds number is, we'd have big U times L over nu. And that's what this is down here on the bottom. So we have drag coefficient as a function of Reynolds number. And this actually looks quite a bit like our Moody diagram. You can see as we increase and we get rougher, so that have roughness increases from bottom to top, then our drag coefficient goes up. We can also see that we have a completely turbulent region where the flow, or so where the drag coefficient is relatively independent of the Reynolds number. We also have a laminar region where the flow is, we can see the drag coefficient decreases with Reynolds number, this transitional part, and then here's a smooth, this lowest line that represents the limit of a smooth turbulent plate. A lot like our Moody diagram. Over here on the bottom right corner, this is a table from the textbook showing the different equations that can be used to model these different curves. The one for laminar flow, which is the 1.328 divided by the Reynolds number to the 1/2, and then you see one for the transition, where again reminding you that the transition is about 500,000. One for the turbulent smooth flow, smooth plate, which would be this lower part here, and then the completely turbulent component. So you can see here at the bottom. So these different equations that you can use depending on what the situation is for your flat plate. Okay, so thinking again now, flat plate is a situation where we're completely dominated by shear stresses, and that the drag force is completely dominated by shear stress, and we integrate that to get the drag force. But in general, if we're thinking about drag over some object, we are going to, as I talked about with the cyclist, be integrating the pressure and the shear stresses over the object. So here we have an airfoil, and usually we'll talk much more about airfoils next lecture, but this is a good illustrative example. You can see that the airfoil is going to have both a pressure distribution and a shear stress distribution, and some upstream velocity here, big U, that we're looking at. And this cursive D that you see here, that represents the direction of drag force, the action, and the cursive L, that's the lift force. So L is the lift direction, and our D here is the drag. And so we're going to decompose these vectors, these force vectors, pressure and shear stress, into those components, so that any of the components acting in the D direction, they will be contributing to drag, and those acting vertically, and usually we think about gravity going the other direction, but you could move this and flip it over and have it be the opposite of drag, which is opposite of gravity. If you flip over your wing, that would normally be giving you lift vertically against gravity, then that would act as like a spoiler pushing down on a vehicle to give it better force to hold it down on the ground as it's going around corners, say, for example. So what we need to do, though, is the basic idea is, as I said, to get that drag force, we are going to integrate the force over the entire surface. So we're integrating the force over the whole surface that we have here. And if we want, and the same thing is going to happen, the integrated force in the lift direction, or in the drag direction, is going to be, which is here, this X direction, that's going to be the drag, and the integrated force in the Y direction, that's going to be lift. And you can see, you can think about it in terms of taking components. So we have, say, for example, this is kind of the illustration from your textbook about looking at the components. But if we have our surface here, you can see, let's look at this drag component here, or this pressure component here. It's going to have a Y component that is pointing downward, and it's going to have an X component that's pointing to the right. So since it's doing this, it's going to have a component that is contributing favorably to the drag, but it's actually contributing against the lift that we have. And so we have to add up all of these little vectors. Down here is an example where now we have a component of the pressure that is acting upward vertically, so that would be contributing to the lift, and it still has a component to the right that's acting to contribute to the drag. And we have to do the same thing for the shear stresses. Here, if you think about this example, we have a component of the shear stress, so we call that tau wall, say, in the X direction, and then a tau wall in the Y direction. So that means that we have one component that's sort of acting a little bit against the lift force and one component that's acting for the drag. And so we break that up by using these cosines and sines around the airfoil. Okay, so we can do that for any of our object shapes that we're dealing with. And the generally will have both components, again, of our pressure drag, sometimes called form drag, and our skin friction or our shear stress drag. Shear drag, skin friction. Okay, so now let's kind of go to more of a what I call bluff body flows. So these are flows, and it's not just me who calls these bluff body flows. This is generally in fluid mechanics, we call them bluff body flows. So flows around objects like cylinders, cubes, plates, where the flow is highly likely to separate under high Reynolds number situations, unlike, say, for example, a nice aerodynamic shape like an airfoil. So here you see on the left-hand side that we have some different cases that we expect for flow around a cylinder. On the top left-hand side, you can see a situation where we have no flow separation. And basically what we're seeing here as we move from left to right and then top to bottom is increasing Reynolds number situations. So here, in this case, we have some separation that has occurred. You have the separation streamline here, and the flow has a wake bubble that is going to be associated with low pressure in the back here. Then we have a situation in very highly unsteady flows as the Reynolds number goes up, where we'll have vortex shedding, and this is called the so-called oscillating Kármán or von Kármán vortex street wake. And finally, we can increase the Reynolds number, and we'll have a very highly turbulent boundary layer in both cases, but maybe we have a laminar boundary layer, okay, where we have separation here, or then we have a turbulent boundary layer over the front of the cylinder, and we have delayed separation. Okay, so we'll talk about all those situations in more detail. One of the fun examples, if you've never seen it before, is the so-called Tacoma Narrows Bridge incident. And so we'll go ahead and take a look at this. Here you can see the example of this bridge in Washington State, that is oscillating horribly. And what happened is the wind is, you can see the bushes kind of shaking at the bottom. The wind is blowing across, and the vertical cables are cylinders. And the vertical cables have a vortex shedding frequency about this. You remember the so-called Struhal number. And in this case, what is happening is that shedding frequency is very close to the natural frequency associated with our bridge, and it's causing it to oscillate immensely. So much so that at some point here, you can see that we get to the point where we're going to have total collapse of the bridge. Unfortunate car that was left on there, as I understand there were no people in that car. But you'll see here in just a moment that we have total collapse of the bridge as a result of these oscillations. And what happens is, yes, the bridge collapses and we have total failure. This is obviously a very short-sighted design of the bridge. And so when you think about designing a bridge, you need to think about the diameter of your cylinder. You need to think about the Struhal number and whether or not the frequency that you're going to have oscillation occurring at is close to the frequency at which you would be expecting the vortices to be shedding. So let's take a quick look at let's imagine now, so I was saying that we have these cables, and if you look down at the top of the cable, it looks like a cylinder, and we have these vortices that are shedding off of the cylinder. And if we look at this example, you'll see here, this is a figure from Van Dyke's book, which shows dye that was released into the wake of a cylinder that is, now we'll kind of look at this as a numerical simulation. And so you can see that we have little small particles being released, and we're tracing out the path. And we had the initial Reynolds number, now we've cranked it up, and now we actually get separation. And what's happening is every time, you can see that these vortices actually oscillate from left to right, or top to bottom, I guess, in this figure, in this animation. And what ends up happening is the pressure is actually changing when this is going on. We'll have a low pressure as it oscillates. One of the sides is low pressure. The vortex sheds, and then the pressure goes up, and then on the other side the vortex sheds, and this goes back back and forth. And so we have an oscillation of, say, low pressure and high pressure regions, and this low and high pressure that go back and forth as the vortices are shedding lead to forces being applied at this frequency. And if that force application is at a frequency that is pretty close to the natural frequency of the bridge, then we can get this horrible situation that occurred with the Tacoma Narrows Bridge. So very interesting real-world example. So let's dig in a little bit more into the details of the flow around a cylinder or a sphere. Here we have a cylinder, and on the left-hand side, we're going to start thinking about inviscid flow. So if this figure doesn't come out well, please make sure you look in Chapter 9. This figure is from your textbook so that you can have a very nice clear look at what this would look like if, for example, it doesn't show up well. So I do apologize if that's the case. It's figure 9.16. Okay, so what we see here is going from left to right, we have this velocity, which is our free stream oncoming velocity. We know that along the center we're going to have a stagnation point here, and the velocity there is 0. It's an inviscid flow, so actually we have the velocity at the wall is not 0 because it's an inviscid flow. And as we go around this surface, the velocity, you can see these streamlines start to get smaller, or not smaller, the streamlines start to get closer together. Remember that if you have two streamlines that come together, this is what is happening here. The flow is actually accelerating. We have constant mass flow rate between streamlines, and so as the streamlines get smaller, if we have constant mass flow rate, then this area effectively gets smaller from here to here, and so the velocity, say here at V2, is going to be much greater than the velocity at V1, and that's what's happening as the flow goes around the cylinder from point A to point C. And as the velocity increases, the pressure decreases, and we see that from Bernoulli's equation that shows us that this relationship exists. So the pressure is decreasing as we go from point A to point C. The other thing that we can do is we can think about Euler-N equation. Here we have, say, increasing pressure as we're going away from if we're going away from our center of curvature, and over here, that means this is sort of lower pressure, and that makes sense. This is our stagnation point, which should have high pressure. But above and the top of the cylinder, you can see the curvature changes. So we have a point where the curvature actually changes, and so the pressure should be increasing as we go away from the cylinder. So this is going to be our low pressure region here, and our high pressure region up here. Obviously, high pressure at the stagnation region. And inviscid flows are really interesting. We also call this potential flow in the sense that we're not going to have separation. There's no way that we can, no viscous forces acting in the boundary layer. So as we go back around the backside of the cylinder, the pressure just recovers, and it recovers entirely back to the pressure that we would have had at the upstream stagnation location. Again, the velocity is going to be 0 there. So again, we follow from point A to C to F. Our pressure decreases, and then it increases as the velocity goes from 0 at the stagnation point. This is our front stagnation point. It goes 0 to the top of the cylinder, and then the velocity goes from 0 to the maximum velocity on the top of the cylinder, and then decreases again back to a stagnation point. We'll call this the trailing edge stagnation point, SP stagnation point. So that's a little bit non-intuitive, but that's the case for inviscid flows. And remember, in inviscid flows, we can get a good idea of what the velocities are over our object, however, using the Euler equations. However, what we can't do is compute drag. That was D'Alembert's paradox that we talked about last class. So what about real flows, viscous flows? So if we have a viscous flow now, we are not going to have what we saw here on the left-hand side. And this is, again, download my slides if this does not show up well. And I'm going to try to zoom in a little bit, so maybe it makes it a little bit better for you. Okay, so here, just like before, we have streamlines coming in from left to right. We have our front stagnation point where the velocity is going to go to 0. And as the flow goes around on either side, now we do have a no-slip condition. We do have 0 velocity at the wall, and we do have a boundary layer, okay? And we'll start out with a thin laminar boundary layer starting to form as it comes from the leading edge and in either direction. And we can see that boundary layer, if we have a thin laminar boundary layer, it will start to thicken. And then on the leading edge, we have a favorable pressure gradient, okay? So that is, if we go back to just what we talked about before, over here, the flow is accelerating, and we have the pressure decreasing with x direction. So here we have, on the left-hand side, we have dp dx is less than 0, and that's a favorable pressure gradient. Whereas on the right-hand side, we had dp dx increasing, and so that's an adverse pressure gradient. So that should give you a hint about what's going to happen. So we have this adverse pressure, or favorable pressure gradient on the front of the cylinder, and once we get to the top, we start to get an adverse pressure gradient, which means the velocities inside of the boundary layer start to slow down, and at some point, we're going to have our profile become tangent, and separation is going to occur. Then after separation, we have backflow that you can see here, and we'll have this wake that's forming. All right, so that's kind of what's going on in the boundary layer with the velocities, but on the bottom half of this figure, let's think about what's going on with the pressure. So just like before with the inviscid flow, we have a stagnation point. That is going to be our region of maximum pressure. The pressure will decrease, and as the pressure decreases, the velocity increases, so we have this favorable pressure gradient, and then at some point in time, the pressure, after we get to the top or bottom of this cylinder, the pressure will start to rise again as the velocity decreases, again following Bernoulli, and that's our adverse pressure gradient. And then once we get to separation, actually what happens is we have a region of constant pressure, and that's in the wake region. And it's a constant pressure that's lower than we would have expected in an inviscid flow. And we are having some technical difficulties here. Okay, back to we have. So on the bottom right, these are these show the different velocity profiles that we would see going from upstream to upstream, moving slightly downstream to the top of the cylinder, to the point of where we expect separation to occur. Remember, separation occurs when du dy at the wall is equal to 0. That's the shear stress at the wall is equal to 0. Very important. Remember it for the quiz. All right, and then here on the bottom right is the pressure, and you can see the dashed line. This represents our inviscid theory, which was what we were looking at for our inviscid cylinder. But you can see then the dark line here, the solid line is turbulent flow, and then the dashed line is laminar flow. And so you can see all of them follow the same rough shape until almost the top of the cylinder. And then once we get to near the top of the cylinder and we have separation, then that's where we have this big difference between the three of them. And all three of them, both the laminar and the turbulent cases, we have this constant low pressure region. What I mean by low pressure is here is our 0 pressure coefficient. That is that the pressure minus the pressure at the stagnation point. We don't ever get back to that. And so now there's a pressure imbalance between the front and back of the cylinder. The pressure here at the back of the cylinder, whether it's laminar or turbulent flow, is less than the pressure at the front. So there's this delta P across the front and the back of the cylinder. The pressure in the wake is less than the pressure upstream, and that leads to a pressure force or a form drag acting to retard the motion or generate a drag force on the object. Okay, see if my technical difficulties can go, whoa, okay, let's keep my annotations and try to continue to move on. Okay, Now, here's an example of kind of what this looks like when it's going over a sphere. On the left-hand side, you have a laminar flow. On the right-hand side, you have a turbulent boundary layer. So in this case, you could maybe say for the turbulent boundary layer, maybe we've roughened the surface. And if we roughen the surface, we can get turbulence to occur much closer to the leading edge. And what ends up happening is if we have a turbulent boundary layer, momentum is transferred down closer to the surface and prevents separation from occurring. So if this is sort of our separation streamline that we have here, you can see that separation is delayed for the turbulent case compared to the laminar case. And so that actually reduces actual drag force. And that's why we dimple golf balls, say, for example. So let's look at this for a second. Say I have a cylinder or a sphere. If we start out with a boundary layer that's laminar and it's thin, then it separates somewhere around here. But so the top side would be laminar. And then on the bottom side, what happens is we roughen it, and what we get is there's more transport of high velocity fluid to the surface because turbulence acts to mix. And it's mixing more of this. Remember, the velocity out here is all big U. This is the free stream. At the wall, it's much less. But if we have turbulent flow, eddies are going to act. So for the turbulent flow, eddies act to mix high momentum fluid to the surface, at least towards the surface. And so as a result, that high momentum fluid is preventing separation from happening because we can't get to the point. So we have a situation where we sort of start out with a velocity profile that looks maybe something like this. And then remember, we get a point that looks like this. And so there's a loss of momentum near that surface when we have that point where we have a tangent, where we have a zero gradient at the surface. So as a result, the turbulent eddies act to delay the separation. Generally, when we look at where the transition is between a turbulent and laminar boundary layer on a natural surface, so that's going to occur where you have Reynolds numbers higher than about 2 times 10 to the fifth. So that is, if your Reynolds number, say based on U infinity, d over nu, if that is greater than about 2 times 10 to the fifth, we'll have a turbulent boundary layer and delayed separation, or we can make that happen sooner with roughness elements. So now we have 3 different turbulent transitions that you need to think about. Pipe flow, that's about 2300. Boundary layer, flat zero pressure gradient boundary layer, that's going to occur, transition is going to occur at about 500,000. And we're going to have it occurring at about 200,000 for flow around a sphere. All right. Here is this classical curve of the drag coefficient versus Reynolds number for either a cylinder or a sphere. So we're talking about both the shear component to drag and the pressure component to drag. And prior to separation, both components are important. And so here at low Reynolds numbers, we know that we have Stokes' law that's important for the drag coefficient, say 24 over the Reynolds number. But then, and that's going to be, when we're 1, so say less than 1 for the Reynolds number, a little bit above that. But then we get separation typically occurring between about 10 and 100 over here. So this separation is occurring between a Reynolds number of about 10 and 100. Then above a Reynolds number of about 1,000, we have this regime of a constant Reynolds number that we've talked about, which is really important. And then we can see this rapid drop, both over the cylinder and over the sphere. That rapid drop in the drag coefficient, that is when we have the boundary layer becoming turbulent. It reduces the drag significantly because what happens, again, we have this wake. The wake gets smaller because turbulence has acted to delay the separation. So originally with the laminar boundary layer, we have this wake that's really, really big like this, but we delay separation so that for our turbulent case, we have a narrower wake. And that results in this drop that we'll see here in the drag coefficients. You can see that for a rough sphere, what happens is that we actually get it to happen earlier. We get a turbulent boundary layer earlier, so we drop the drag coefficient at lower Reynolds numbers. Again, why we dimple a golf ball. And then you'll see as the Reynolds number gets higher, eventually we get to the situation where slowly the wake starts to enlarge and the drag coefficient goes up again. So a really important kind of physical understanding of what's going on for flow over a sphere or a cylinder. And then this is just kind of a little bit of a reminder of exactly when this is occurring. So separation is going to occur for a turbulent boundary layer. So we have the flow coming in, it goes around and then separates, and this will be our separation point that we have here. And if we think about what's going on now, we'll have, these are streamlines, separation streamline that occurs here, and then you have your wake that's occurring here. This is going to happen at an angle of about 120 degrees. You can see that for the laminar case on the bottom, it happens way earlier. So we have this much larger wake that occurs. And again, same kind of idea. We're going to have this separation zone. So these are the streamlines. And just an important reminder, I haven't talked about it a lot in class, but streamlines really can never start or end in space, so they kind of have to just keep going. They're not allowed to, they can end at a surface, but they can't just kind of end in space. Conservation of mass really doesn't allow for that to happen. We can if we have a sink of mass or a source of mass. Just a bit of a side note there. Okay, so back to our sphere flow separation. So we can't determine the separation points really analytically. The point is not fixed. You saw when we were looking at the flow around, the simulation of flow around the cylinder, that this point moves back and forth depending on how the vortices shed. On average, they're about 120 or 80 to say 90 degrees for the laminar boundary layer. And we have to get this either experimentally or from very carefully run numerical solutions to the Navier-Stokes equations. Okay, let's see if we can move forward. All right, my technical difficulties again. It's not wanting to move forward. We'll try one more time. And we may have to restart this PowerPoint. Let's go ahead and, my son's skiing. I'll go ahead and restart this PowerPoint. I apologize. And move back on to where we are. So there we go. Okay, so now we're going to go and have a look at an example that I'd like to work on. So this is a real-world example. Let's go ahead and compute, say, for example, power, drag force, and fuel consumption associated with a car, because this is something that's very important. Why I'm using a 2007 Honda Accord, because this was something I could easily find the information on. Here, the projected width of the Honda Accord is about 1.75 meters, and the height is about 1.42 meters, and the drag coefficient is about 0.29. So let's go ahead and work out an example here. So if I get my notes back up again. So we want to first start out by determining what is the drag coefficient, the drag force. Now, what kind, a vehicle is generally a bluff body. So when we're talking about the drag force around a bluff body, what we're going to find in general is that the drag force that we have for a bluff body as a function of the velocity is has a parabolic increase. That is, this drag force increases proportionally to the velocity squared. Well, that should give us a hint also, and we can determine this experimentally. That gives us a little bit of a hint towards fuel consumption, because if we think about the total fuel consumed, that's going to be proportional to the total work we do, which is going to be the force times some distance. And so we can see that as we increase velocity, that work that needs to be done, the total work is going to go up with the velocity squared. So that's going to play an important role when we think about what speeds we drive at and how we get fuel consumption, what's going to, the impact of velocity on fuel consumption. So the drag coefficient, though, that we look at is, as we've talked about before, simply the drag force divided by 1/2 rho v squared times the projected frontal area. And if we have, for example, a sphere, then say for a sphere, so it's our projected frontal area. So for a sphere, then A is just going to be pi d squared over 4. This is our frontal area, say, for a sphere. So if we have drag, if we're looking at drag around a bluff body, then this is the kind of curve that we would expect for the drag force. And the drag coefficient would be dominated by this sort of, would be written in this format, drag force divided by 1/2 rho v squared A. And this is, again, a situation where we have a pressure-dominated drag force. And flow around a vehicle is a situation where we have a pressure-dominated drag force. All right, so how are we going to kind of think about this example? Well, actually, so we now know that our drag force, we can rewrite the equation as 1/2 rho v squared CD times A. And given that we can use this equation, we have a lot of information to be able to compute the drag force based on what we've been told. We can do that. Now, how do we compute, say, for example, the power? Well, we need to use the integral energy equation. And we go ahead, and if we have our vehicle going at a constant, this is going to be my terrible drawing of a vehicle, but we have our vehicle that's moving along at a constant velocity. And then we can draw our control volume around this, and the work that's going to be done, the shaft work, is going to be equal to the drag force that is imparted on it. So that is, well, the work rate associated with the drag force. So what is that? That's going to be the shaft work that we'll have is going to be equal to the force times the velocity. Okay, so this is our drag force, net drag force times the velocity. So what does that end up being? Well, we can say that this is the power that's going to be required, is the shaft work. And that's going to be equal to 1/2 rho. Now it's going to be v squared times v, because we have this v here, 1/2 rho v cubed times CDA. So the power required is proportional to the speed cubed. So that means small increases in velocity of your vehicle result in very high increases in the power required to maintain that velocity. Anybody who's a cyclist knows that if they've ever measured their own power. Okay, so let's look at our Honda Accord example again here. Here, I'm going to start by asking the question. The first question is, determine the drag force on the Accord for a constant speed of 55 miles per hour. Okay, something that we'd be interested in determining. So the forces acting against the vehicle include other things like road friction that we would have. However, we're only going to look at the aerodynamic losses that are going to be contributing to our resistance. So let's go ahead and calculate the drag force and the power required to go at 55 miles per hour. Okay, so determine the drag force and power. So drag force, and we'll compute the power. So the drag force is simply going to be equal to 1/2 rho v squared CDA, and we have our, we're at sea level, and if we're at in Salt Lake City, it'll be a little bit lower. So if we're at sea level, so rho of air at sea level, that's going to be 1.2 kilograms per meter cubed. 1.2, times our velocity, which is 55 miles per hour, which if we do the conversion, that's about 25.6 meters per second. 25.6 meters per second squared, times our drag coefficient, which we were told was 0.29, which is quite low, times our area, which is going to be equal to 1.75 times 1.42. And that area that we have, the projected area, is about 2.5 meters squared. So if I go ahead and compute this, my calculator fell down. So we go ahead and compute this, we get the following. So 1/2, let's see, sorry. If we compute this, 25.6 squared, 0.29, 2.5, 1.2 times 0.5. So let's see. Apologize. Should have done this previously, but I only did it for the power. So 25.6 squared times 2.5 times 0.29 times 1.2 times 0.5. So we get about 285 newtons. Okay, so this would be our drag force. At least that's what I get in working it out. You can work it out and make sure I didn't make a mistake, but I think that looks right. Now what we need to determine is the power. So what is the power required to maintain 55 miles per hour when we're only to overcome the drag force? So that's going to be our W dot shaft. That's going to be the power. And that's now going to be 1/2 rho V cubed times the CDA. So again, 1/2 times the 1.2, now times 25.6 cubed meters per second, times the drag coefficient of 0.29, times the area, which I said is 2.5 meters squared. Leaving my units out, I apologize. So if we work that out, in this case, now I get 7,300 watts, or 7.3 kilowatts. And so maybe that doesn't mean a lot to you. Many people think in horsepower with vehicles. So what is that? So we know that 1 horsepower is about 746 watts. So if we divide that by, if we divide 7,300 by 746, we get, it's not quite 10, we get 9.8 horsepower. So not very much, actually, to maintain a speed of 55 miles per hour. So relatively aerodynamic vehicle going at a relatively low speed will end up having a relatively low power requirement. Now, what about fuel economy? So that's the next thing that we want to look at. So this is going to be the third part. So we'll ask this question. So if the power of an automobile is increased, if the power of an automobile is increased by 25%, 25%, what percent increase in speed of the vehicle can be expected? So what speed would be expected? Now, this is going to be based only on drag force as the resistance. Okay, so any other resistance associated with rolling resistance, we're also not accelerating. We're just looking at a constant speed, one constant speed to another constant speed. And the increase of the power, though, is 25%. So let's go ahead and do the same kind of idea of what we did before. Now we're saying, so the power has increased by 25%. So that means, say, W.2 over W.1 is equal to 1.25. So that is, our increase in power is 25%. So going from speed 1 to speed 2, we've had an increase of 25%. So that's what the 2 and 1 equal. So we can work this out. We have here 1/2 rho v cubed times c dA. And this is for velocity 1. Everything else is the same. And then we'll have for the power 2, we'll have 1/2 rho v2. Oops, sorry. Numerator, first of all, that cubed is not very good. So let's make that cubed better, a little bit better. So 2 is on top and 1 is below times CDA. Now, we're going to assume that CD is constant with velocity. So assume CD is constant with velocity. What does that imply? That implies that we're in sort of some part, say we have a drag coefficient as a function of Reynolds number, and it does something like this. It assumes we're in this part of the curve where the drag coefficient does not change largely with the Reynolds number, which is not a bad assumption. All right, well, let's take a look at, oops, we need a cube down here in the denominator. So let's go ahead and look at this. So obviously, no real changes in density, no change in the drag coefficient we've assumed, no change in the area. So what we see, we're simply left with that the ratio of the power, so W2 to W1, is 1.25. That means that the ratio, that is going to be equal to the ratio of the velocity. Oh, man, I'm doing a terrible job with keeping straight my superscripts and my subscripts. The velocity cubed at the higher velocity divided by the velocity cubed at the lower velocity. So what does that mean? Well, let's go ahead and solve for V2. So that says that V2 is going to be equal to 1.25 times V1 cubed, take the cube root of all of this. And if we do that, well, we end up with that V2 is equal to, well, the cube root of V1 cubed is just V1. And then the cube root, then we have to take that times the cube root of 1.25. So that's going to say that V2 is equal to V1 times 1.078. So that means that the velocity has V2 is going to be V2 is 7.8% greater than V1. So that, what does that imply? So we increase power by 25%, and we only get a 7.8% increase in velocity. That's a real bummer. I mean, it seems this is this diminishing returns, and it's kind of painful for us. So what does this say about fuel economy? So let's ask that question. What does this say about fuel economy? All right, well, and let's make the question a little bit more specific, make it kind of relevant. When I was a very little boy, the maximum speed limit was 55 miles per hour. Now here in Utah, it's 80 miles per hour. So how does the speed limit play a role? All right, so let's compare that. So let's look at 80 miles per hour versus 55 miles per hour. Okay, so 80 miles per hour, if we convert that to our SI units, that's 36 meters per second, and 55, as we said before, was 25.6 meters per second. All right, well, let's go ahead and do the same thing that we kind of did before. Now, we're talking about fuel consumption, and fuel consumption is going to be proportional to the number of joules of work we do. So fuel consumption is going to be equal to the work we do. It's not exactly equal to the work we do because we have inefficiencies and things like this, so let's say it's proportional to that. This is sort of like, the work we do, like the number of calories we burn is proportional to the amount of work our body does, and so if we just focus on the aerodynamic drag component of this, this is what we can get as a result. So again, focusing only on aerodynamic drag, then the work that we're going to be doing, now this is not the work rate, the work is the force times the distance. So our drag force is, again, 1/2 rho v squared CdA. We talked about that before, times the distance that we travel. So what is the ratio of the amount of work that has to be done at 80 miles an hour compared to the amount of work that has to be done at 55 miles per hour? So that would be, say, work at 80 divided by the work at 55. So 1/2 rho v squared, so I'll call that 80 v squared CdA times the distance. Again, 1/2 rho v, say, 55 miles per hour squared CdA times our distance traveled. Okay, so again, this is just so that when you ask me, this is the distance traveled. Okay, so our distance, oops, one too many L's there, but I think that's okay. All right, so what does this mean? Again, if we assume CD is constant, then we're only left with the ratio of the velocity squared, but this is a very big deal. So if we look at this, then the work at the work, or the amount of energy consumed to go 80 miles per hour, to go this distance for 80 miles per hour, compared to the work required to go the distance d at 55 miles per hour, is going to be equal to v squared at 80 divided by v squared at 55 miles per hour. And if we can, just go ahead, and I can't do anything in English units, so we'll do this in metric units. So it's the ratio of 30, it doesn't matter, right? It's 36 squared to 25.6 squared. And this is, and this is about 2. So I'll work this out exactly here on my calculator, but it's very darn close to 2. We have 36 squared divided, which is 1296, divided by 25.6 squared, which is divided by 655.4. And as you can see, it's very, very close to 2. So what do I get? I get 1296 divided by 655.4, and it's about 1.997. So 77. So if you think about this from just the aerodynamic drag point of view, if you decide to go 80 miles an hour, you can see that the fuel economy is about half of what you would be for if you were to go 55 miles per hour. So this is why, back in the 70s, President Jimmy Carter had proposed lowering the speed limit to save fuel during the first oil crisis that we had. Okay, so hopefully that was a fun lecture and gives you some interesting understanding and exciting understanding about drag force. And our next lecture will move into lift, and specifically lift and drag associated with airfoils. Again, what I think is an important, fun lecture.